To the video lecture on power system analysis and stability. In this video, we are going to look into the second problem of the Gauss-Seidel method. The first problem, we have seen 3-bus system. In this 3-bus system, all the 2 buses were PQ buses and 1 bus was a slack bus in the problem 1. And in this problem, we have 1 slack bus, 1 PV bus and 1 PQ bus. Earlier problem, both the buses, both bus 2 and bus 3 were PQ buses. Here, one is PV bus and other one is the PQ bus. As discussed already, PQ bus in the sense both P and Q will be given and we want to find out E and del. PQ bus, for PQ bus, both P and Q will be given and I want to determine the magnitude of the voltage and its angle delta. This is PQ bus. In the case of PV bus, P and voltage magnitude will be given and I want to determine Q and delta. This I want to determine. Very importantly, this Q in the PV bus will have some limits as given here. It is between 0 and 4. This should lie between 0 and 4 in order to maintain this E at a constant value. So, the given problem, bus 1 is a slack bus and E is specified, which is given as 1.05 angle 0, and bus 2 is a PV bus. E is specified as 1.2 per unit and the power generated P is given as 3 per unit, and bus 3 is a PQ bus which has both real and reactive power of 4 per unit and 2 per unit respectively. I want to calculate the load flow solution for one iteration by using Gauss-Seidel method, and the Q limits of the generator 2, as I already specified, if in the case of PQ bus, Q will be specified within the limits and the Q limits of this generator 2 is mentioned as 0 and 4. Minimum limit is 0 and maximum limit is 4. And the acceleration factor alpha is given as 1. So to this problem, we want to solve the load flow solution for one iteration using Gauss-Seidel method. As a first step, I want to determine the bus admittance matrix. So I want to find out the Y bus matrix for this given 3-bus system. As it is a 3-bus system, let me write the buses in the row wise as well as in the column wise. So row wise, it is 1, 1. So the branches or the transmission lines joined at this bus 1 is 2 minus J5, 1 minus J4. These two. So I want to add these two. This becomes 3 minus J9. 3 minus J9. And for the between 1 and 2, between the bus 1 and bus 2, I have 2 minus J5. I want to take the conjugate of this. Between bus 1 and bus 2, the admittance is 2 minus J5. I have to take the complex conjugate of this. So this becomes minus 2 plus J5. Minus 2 plus J5. And between bus 1 and bus 3, I have 1 minus J4. I have to take a complex conjugate of this. Then that becomes minus 1 plus J4. Minus 1 plus J4. So this is the bus admittance matrix of the first column, first row. And for the second row, similarly, I can take between 2 and 1. Again, I have 2 minus J5. I have to take a complex conjugate of that. That becomes 2 plus J5. And to the second bus, the elements connected are 2 minus J5 and 2 minus J9. When I add those, it becomes 5 minus J14, 5 minus J14. And between bus 2 and bus 3, I have 3 minus J9. I have to take a complex conjugate of that. That becomes 3 plus J9. 3 plus J9. And similarly, between 3 and 1, I have 1 minus J4, so I have to take a complex conjugate. That becomes minus 1 plus J4, minus 1 plus J4. And between 3 and 2, I have 3 minus J9. I have to take a complex conjugate. That becomes 3 plus J9, 3 plus J9. And at bus 3, I have two elements, 1 minus J4 and 3 minus J9 are connected. I have to add these two. That becomes 4 minus J13. 4 minus J13. And the voltage magnitude of all the three buses are given. That is, the voltage magnitude of bus 1 is given as 1.05 per unit, which is 1.05 plus J0. I can write it as plus J0 because the angle is 0, and the magnitude of bus 2 voltage, that is the magnitude of bus 2 voltage, is given as 1.2 per unit. 1.2 per unit, I can write it as 1.2 plus J0, 1.2 plus J0, and the E3 voltage is not given, so let me assume it as 1 per unit. That becomes 1 plus J0, 1 plus J0. So the first step in the algorithm is to calculate the Y bus and try to write the values of all the three E1, E2 and E3 respectively. As I have already mentioned that the reactive power at bus 2 has a limit. So the reactive power at bus 2 is having a limit of 0 to 4. 0 to 4. So to check whether this is Q2 power, that is reactive power at bus 2, is lying within the limits, I have to use this expression by substituting P is equals to 2. So substituting P equal to 2 gives me Q2 is equal to minus imaginary part of E, P is 2. So E2 star summation of Q equal to 1 to N. N denotes the number of buses. Number of buses is 3 here. So this becomes E2 into Y21, P is 2, Q is 1. Y21 into E1 plus Y22, now Q becomes 2, Y22 into E2 plus Y23 into E3. Y23 into E3. So here E2 star indicates the conjugate of this E2, and Y21, Y22, Y23 the values of the second row of the Y bus matrix. E1, E2, E3, all the values are given here. So substituting all these values, we will get minus imaginary part of E2 conjugate, that is 1.2 minus J0 into Y21. Y21 is this element, that is minus 2 plus J5. So that becomes minus 2 plus J5 into E1. E1 is 1.05 plus J0. So 1.05 plus J0 plus Y22. Y22 is 5 minus J14. So this becomes 5 minus J14 into E2. E2 is 1.2 plus J0. 1.2 plus J0 plus Y23. Y23 is minus 3 plus J9. So this becomes minus 3 plus J9 into E3. E3 is 1 plus J0. 1 plus J0. So let me try to calculate all this, and finally this will become minus imaginary part of after simplification of all this complex conjugates and complex variables, I will get finally imaginary part of 1.08 minus J 3.06. 3.06. So imaginary part of that, if I take it, then Q2 becomes 3.06. 3.06. So the value of Q2 should lie within the limits of 0 to 4. So this is within the limits. So I can take this as the value of Q2. This is step 2 of the algorithm. Now step 3. Step 3 is to calculate the voltage magnitudes of the bus 2. So bus 2 and 3. So let me substitute. This is the expression which we have used for calculating the voltage magnitude of the buses of the zeroth iteration or first iteration. So now let me substitute P is equals to 2 and K is equals to 0. P is equals to 2 is the bus in which I want to calculate the voltage magnitude, and since it is the first iteration, I put K is equals to 0. So by substituting this, I will get E2 is equals to 1 by Y22, because Y22 YPP is Y22 into P2 minus J into Q2 Q2 minus J into Q2 divided by E2 of 0, E2 of 0 its conjugate minus Q is equals to 1 to, now P is equals to 2, 1 to 1. So this becomes minus Y to 1. P is equals to 2, Q is equals to 1 because 2 minus 1 here becomes 1. So Q is equals to 1 to 1. Q is equals to 1 to 1. So Y to 1 into E of 1 of E of 1 0, E of 1 0 minus Q is equals to 2 plus 1. Q is equals to 2 plus 1, that is 3, and the N is the number of buses, which is also 3. So Q will be 3. So Y 2 3 and E3 of 0. E3 of 0. So this is what the expression for E2. So when I substitute this, this becomes 1 by Y22. Y22 element is this. This is the element of Y22. So 1 by Y22 is 5 minus J14. 5 minus J14 into P2. P2 is the value given in the problem of the bus 2. That is, the power generated at bus 2 is 3 per unit. So this is 3 minus J into Q2. Q2 is what just now we have calculated, which is 3.06. So 3 minus 3.06 whole divided by E2 naught. That is the voltage magnitude of bus 2 at the previous iteration, that is 1 plus 1.2 J0, its conjugate. So this becomes 1.2 minus J0 minus Y21. Y2n element is this one. So this becomes minus 2 plus J5 minus 2 plus J5 into E1. E1 of the 0th iteration or first iteration, whatever it is, the previous one. So E1 is 1.05 plus J0, it is 1.05 plus J0, 1.05 plus J0 minus Y23. Y23 element is this. So this is minus 3 plus J9 into E plus J9 into E3 naught. That is the voltage magnitude of bus 3. Voltage magnitude at bus 3 is 1 plus J0. So that is 1 plus J0. So this is the expression for E2. So when I simplify this, and finally I will get E2 magnitude as 1.236 plus J 0.10216. So this is the expression for E2. So E2 at first iteration. E2 at first iteration is this expression or this value. So I want to find out the change in E2, that is delta E2, which can be written as E21 minus E2 naught. E21 minus E2 naught. So E21 is this expression, that is 1.236 plus J 0.010216 minus E2 naught. E2 naught is 1.2 plus J0. So this becomes 1.2 plus J0. So this minus will come inside. So this becomes delta E2 is equals to 1.236 plus J 0.10216 minus 1.2 minus J0. So this, if I simplify, then I will get delta E2 is equals to 0.03688 plus J 0.10216. So this is delta E2. This is the change in the value of the voltage at the bus 2 magnet. Now the final value of E2 at the first iteration is given by E2 naught, that is the expression of the voltage at bus 2 in the previous iteration, plus alpha, the value, which acceleration factor value which is given in the problem, into delta E2. Now alpha is given as 1 in the problem, so E2 at the previous iteration is 1 plus J0, 1.02. 1.2 into plus alpha is 1 into delta E2. Delta E2, this is this value, that is 0.036 plus j into 0.102 multiplied. So if I get the final value of E2 dash, the value of E2 dash is 1.2368 plus j into 0.10216. If I put it in the polar form, this becomes 1.2411 angle of 4.722. So this is the expression of the voltage at bus 2 after the first iteration. One point is very important to remember here. This magnitude, since it is a PV bus, this magnitude will not change, which means that it will be always 1.2 only. Only the angle will change. So I can rewrite my E21 as 1.2, which is the magnitude will not change, only the angle will change. Angle is now 4.722. Angle is now 4.722. This becomes 1.196 plus j 0.0988. So this is the final expression of the E2 magnitude during the first iteration. In a very similar way, I have to calculate for the third bus, that is P equal to 3 and K is equals to 0. So when I substitute these two in the previous expression, I will get E3 of the first iteration is given by 1 by Y33 into P3 minus J into Q3 divided by E3 of 0 conjugate, E3 of 0 conjugate minus 1 to 2. So 1 to 2. So this becomes Y31 into E1 minus Y32 into E21. This expression will not be valid because when I put P is equals to 3, Q becomes 3 plus 1, 4. 4 number buses is not present. So this expression will not be valid. So this is the expression for E31. So E31 becomes 1 by Y33. Y33 is given as 4 minus J13. So let me use it here. 4 minus J13 into P3 minus J into Q3, which is given in the problem. You can just look into that. This is the third bus. P value is 4, Q value is 2. So this is the value which I want to use it here. 4 minus J2 divided by E3 naught, that is the previous value of E3, which is 1 plus J0, its conjugate. So that becomes 1 minus J0 minus Y31. Y31 element is, you can just look into that. This is minus 1 plus J4. So let me write it here, minus 1 plus J4 into E1. E1 magnitude is given in the problem as 1.05 plus J0. So this becomes 1.05 plus J0 into minus Y32. Y32 element is minus 3 plus J9. So this is minus 3 plus J9 into E2 of the previous value. E2 of the previous value is 1.196 plus J 0.0988. So that I want to use it here. 1.196 plus J 0.0988. So when I use all these expressions, and finally I will get E3 of the first iteration is 0.919732 minus J 0.166716. So this is the expression for E31. This is the expression for E31. Now I want to find out the change in E3, that is delta E3 delta E3. Delta E3 can be found out by E31 minus E3 naught. After finding out delta E3, then I want to find out E31 again, which is the final expression, by taking the alpha into consideration, which is given by E3 naught plus alpha into delta E3. Alpha is given as 1. So when I substitute this, I will get finally the expression of E31 as 0.919732 minus J 0.166716. So this is the expression for E31 of the first iteration. So this is how we calculate the magnitudes. Now again in the next iteration, I want to go for calculating the E2 by putting k equal to 2. Again, I will calculate how long I have to go till my previous iteration value of E2 and the present iteration value of E2. If there is no difference, then I can stop my iteration. Or I can fix how many iterations I have to go by fixing the value of k, and that is also the another method of terminating the iterations. This is how we have to go till the last. So again I have to calculate E3. All the bus magnitudes, if it is not changing with respect to the previous iteration and the present iteration, then I can stop my iterations. This is what all about the Gauss-Seidel method of load flow analysis. Thank you for your listening. Thank you.